Now, I would like to show you really a very important result, which then put in perspective really the role of scaling operator, in particular the relevant scaling operators. So what I want to show you is the following. Historically and phenomenologically, people have tried to characterize phase transition looking for response function of order parameter in laboratory. So what I mean is, imagine you have a magnetic system, then you look the magnetization at certain point, this will be the order parameters, you vary your Hamiltonian, and you see if at a certain point the quantities start to become crazy, namely crazy having some scaling behavior, some branch, some non-analytic behavior. People in the past have characterized this craziness of natures in terms of exponents, namely they put, is an assumption, that they have power law behavior, because in principle you can imagine all craziness around, and then you parameterize the scaling behavior in terms of certain exponents that will be called critical exponents. So historically, all phase transition is encoded into the critical exponents, and these change if you change the group of symmetry behind. So the critical exponents of Ising in d dimension will be different from the critical exponents of post-model in d dimension, and so on and so forth. These exponents depend also on the dimensionality, and they are the fingerprint of the classical universality. Now this is what is about in lab physically, how to say phenomenologically. Now the things I want to show you is that all critical exponents are algebraic equations, are algebraic expressions of the scaling dimension. Okay? So first I will introduce you some simple exponents, and then I'm going to show you in generality that all the phenomenological exponents that experimentalists measure in lab are nothing else than algebraic combination of the delta, the anomalous dimension delta. So from this point of view, as a theoretician, I need to focus my attention on delta. Clear? This is the logic. So first I introduce the quantity that are, but then I show you that they are derived quantities, the basic one and the delta. So let me give you some example taking the Ising class of universality in which I have J and B, remember? However, J is a disguised number for temperature, because when I do partition function, I always have this quantity divided by T, let's say. So I can take as my new variable, rather than J over T, I take T itself. Okay, it's a measurement of T. And B, you can think measure in terms of temperature if you want. Okay? So, you can ask how your correlation length diverge nearby the critical temperature. Well, it goes like T minus Tc to some power nu. So this is what you find in the book like Stanley and books of phase transition. Namely, your correlation length will have a power law behavior around T equal Tc. Now you can prove by thermodynamics that the exponents above and below has to be exactly the same, because a priori you could have something like this, so divergence of different type real, but you can prove by thermodynamics that it has to be the same. However, the coefficient in front is not the same. Okay? Now this is very important because in the theory of phase transition, you do not only compute critical exponents, which are universal, but you can make universal ratio, which are a fingerprint of the classical universality. For instance, if you take C plus divide C minus, This is a universal number, which not necessarily is 1. So for instance, in the tricritical Ising model, this number is 2 cosh pi over 18, which is 1.28, blah, blah, blah. So crazy numbers, but they are the fingerprint. So if the experimentalist measure just this ratio, find 1.28, he knows for sure that it's not Ising, but it's another class of universality. Okay? Okay, so this is the first example, and this defines the first critical exponents. Then you have indeed behavior of the order parameters, which goes like R for delta. So this defines indeed the scaling behavior of this. Actually, let me define 2 delta so that I'm consistent with the previous notation. You see, from this point of view, the dimensionality of the order parameters is L to the minus delta, which is indeed one of the formula have been written before. Okay? Then you can ask also what is about the specific heat. Specific heat is derivative of the internal energy with respect to T, and also this is a quantity which diverges nearby the critical point in 2 different ways. Once again, alpha has to be the same above and below the critical point, the amplitude in front not necessarily. The ratio is universal. Since this guy is also dimension full, you can cook also with the previous C to construct some other universal ratio. Okay? You can keep going because this behavior, by fluctuation dissipation theorem, is also associated to the critical behavior of correlation function, because this is integral dx, the 2-point function or the conjugate variable to the temperature, which is the density energy. Okay? So this goes together because if this guy has to diverge, you see immediately that this correlation function has to go power law. Because if it goes exponential to 0, you never have divergences. Okay? So the 2 things match together. Now you can keep going. So you can have, for instance, susceptibility is how your magnetization change with the other field B, and this once again has 2 different behavior. And so on and so forth. So this once again is dictated to correlation function of the things. Then you can have, for instance, what happened to the order parameters when you are B equals 0, and this vanished. Let me call S the quantity in front, Tc minus B with some exponents B. As well as you might have the equation of states at the critical point, which is how the magnetic field depends on the magnetization when you are at T equal Tc. Now you see that usually when you are away from T equal Tc, you have a linear response. You switch on a little bit magnetic field, the magnetization change little. But if I'm nearby the critical point, it's enough that I give a little magnetic field that I have an enhancement of the magnetization. So no surprise that there is an anomalous relation between the 2 quantities. Okay? So all this, you can define many, many others of that. By the way, you can look a full discussion of all this and the role of universal ratio, which here I have no time to emphasize, in a paper of myself, together with Fioravanti and Pascal Simon is some PRE on probably some years ago, probably 15 years ago, and he's discussed in detail as an example, and non-trivial example, all the calculation on the class of universality, universal ratio, the tricriticalism model. Have a look because it's an example tricriticalism model, but the technical and the idea is plain, you find in detail here. So the message is, given a class of universality, like easing pods and so on and so forth, you have a bunch of exponents So let me write down here. So imagine that you have solved exactly the model. Baxter does. So if you go on Baxter book, you just check the exact solution. Of course, you can derive the exact quantity I'm talking about. So alpha for easing is 0, but for tricritical easing is 28/9. For pots is 11/13. Beta for easing is 1/8. For tricritical is 1/24, for pots is 1/9. Gamma is 7/4 for easing, 37/36, 13/9. Delta is 15 for easing, 77 divided by 3, 14 here. Nu is 1, 5/9, 5/6. So this is 1/16, 3/80, 1/15. Okay? No, yeah, thanks. This is, of course, in D equal to. Yeah. Okay? So the aim of this table is to show you that, first of all, you can compute it. And in some cases, you can compute it exactly. The second thing is that in D equal to, the values are rational. This is an important signature of the story. Moreover, they change if you change the class of universality. Okay? So this is the message. The message is, if an experimentalist measures this response function in lab, making a double plot fit, from the slope, he should be able to derive the quantity I'm talking about. And the output of this work will be, first of all, they change if you change the class of universality. So provide him or her a way of saying, this sample has to be tricritical easing, not easing. Okay? Moreover, in this case, they turns out to be rational numbers from the exact solution. So what I want to show you here now is that all these beautiful numbers and many others that you can define simply by response function are nothing else, alpha, beta, gamma, and delta, that rational function of the delta of the relevant operators. Okay? This is what I want to show. And the argument is pretty nice, because encoded really the core of a normalization group idea. So this is the reason why I would like to present, because once we have clear the idea what's going on, then we can proceed with the technicality, conformal field theory, and this and that. So this is the reason why today I'm insisting on all this part in such a way that we have a very clear physical picture of what's going on. Okay, so the proof goes like this. The proof is around one fixed point. So this is one of my fixed points. I would like to describe all the theories which are nearby there. So is a good approach to parameterize my theory in terms of an action which refer to the actual conformal field theory, that later we are going even to write explicitly, but at this point I don't care, plus adding some operators which drive me the system either away or are entering in it, depending if the operators are relevant or irrelevant. So I'm including here all possible fields which live there. By the way, one of the most important problems of conformal field theory is classifying the operator content around each point. So back in my mind means I know exactly which operator can live there. I know exactly what I'm adding, okay, back in my mind. I have to prove later. But at this level means that if you give me a conformal field theory, I can identify the set of operators, so all the spectra. I know all their properties, so this expression is meaningful, means I can make sense perturbatively, I can make sense in many, many different ways. Okay, that being said, these are the scaling operators, so let's do again now. I transform my x in this way so that my lattice space behind is enlarged b times, and the property of this scaling operator is that they transform in this way, this definition, okay? And the coupling associated to it, the transform as gi b d minus di. Okay? Now, let's take seriously the approach of a normalization group, namely, nothing should change if simultaneously I change the lattice and the coupling constant space. So the partition function should be independent. So imagine that I have a partition function given by some path integral on this action. Of course, at this level is very vague. I don't know what the measure is, what are the relation with the phi operators, but the idea exists. So it means that I'm putting under the carpet all technicality, but I don't care, because what I really care is that if I was able to perform this by extensivity of free energy, this will end up in something like n, the number of blocks, times some free energy per unit of blocks, which will depend on my couplings at the size of my lattice scale A. Okay? Now the point is, now I'm going to make a rescaling of B. So my lattice is becoming B times larger. So the number of blocks have been reduced B minus D, and the coupling constant has been reduced correspondingly. So if I do a renormalization group trajectory, I should have something like that. Okay? Namely, the number of blocks is going to n prime, the coupling constant has changed, but the physics has not changed. So for what concerns free energy, I should have these things here. Therefore, I have a functional equation for the free energy, because n prime is n b to the minus d. So my functional equation is free energy as a function of the coupling constant g is going to be b minus d f expressed in terms of b d minus delta gi. It's clear? Clear? So the nice thing is that you can solve in full generality these function equations. So you're looking for a function, f, such that if you rescale its variable in this way, the function change b minus d is a functional equation. The solution can be given in full generality and consists in this. So you have many different couplings. Now, obviously, if you start iterating this, because this is just one step of iteration, I can keep going. If I keep going, what is the result? That all the relevant operator is going to die sooner or later. Okay? So essentially, I can keep out of the discussion unless I'm picky to compare, say, some numerical data, Monte Carlo and so on, with some field theory formulation. What I want to say is that, let me open and close parentheses, it's true that irrelevant operator, the name itself means irrelevant, you don't care. But there are what is called a dangerous irrelevant operator. Means that the original coupling constant to which they are conjugated was huge, enormously. So to reduce to zero required many steps. So if you do your Monte Carlo certain things, you might see that your data are spoiled by extra effect due to irrelevant operator, but this is because they were dangerous irrelevant. But this level, being the privilege to be a theoretician, I cannot care less. Say, I will iterate it many times. Irrelevant operator will keep out of the way. So this means it's an equation which involves relevant operator only. So what is the solution? The solution is I have kappa relevant operators. In general, in any class of universality, the number of relevant operator is finite. The number of irrelevant operator is infinity. Okay? But the number of relevant is finite. So you have kappa of them. Now, you can have many different ways of writing down the most general solution, depending which coupling you select out to be the one that at the end will be non-zero. What I mean is, imagine you have easy model, you can have T different from TC, but you can have B different from 0. So all the quantity will have an anomalous behavior once you keep one coupling constant slightly away from the fixed point, the other 0. Look my example. Here I'm saying, how is the specific heat? Goes with temperature. I derive by T, of course B is there, but I put B equals 0, but not T. Not T equal TC. So I'm looking how is approaching the things along one direction. Clear? So what I want to say is that you might approach a fixed point by many different, or better, you can go away from your fixed point among many different relevant operators. So the way you write down your free energy, which are all equivalent, by the way, is simply for convenience, you decide, look, the things which I'll never go to switch to 0 is G1, let's say. Means that you keep all the other, you make the derivative, then you put all to 0 but 1. Okay? So with this assumption, the general solution can be written like this. So imagine I select out Gi as the coupling constant which I put to 0, the last one. The free energy which satisfies this is Gi minus d minus di, times a function that you're never able to fix, but you know the functional dependence of it. The functional dependence is Gi divide Gj. Okay. So the status of the thing is, imagine that you have to solve the wave equations. Okay? Imagine that you have to solve, this is a differential equation, that is a functional equation. But, so you know that the general solution of this equation is given in terms of two generic functions given in this way. So what I want to say is that the equation fixes the functional dependence of the variable, in this case x and t, but never tell you which function it is. Any function which depends on this satisfies these things. Here the story is the same. The story is the normalization group for my theory never able to fix the free energy, because depend also the initial condition, everything. But can tell you how it depends on the coupling. And depends on the coupling such that satisfy the scaling equation. So the thing is, you select out one of them. You see, I can interchange. Here I put GI, but you can choose G kappa, whatever. The rest is depend on ratio on the coupling constant. Ratio rescale with a very definite coupling. Very definite exponents. Okay? You can check that if you substitute there, identically satisfied. Yes?
Where has B gone in this form?
B has gone because it's been absorbed by here. B enter in different context. Now remember that when you rescale B, B appear because G goes like G, B minus D, and so on and so forth. Okay? Indeed, if you do it, just is written there. This become B minus D times something which is, yeah, okay? Clear? So this fixed the functional dependence of the free energy.
We have 2 minus delta because D equals 2.
Yeah, you are right, yeah, sorry. I always screw this, but let me put here. Yeah, thanks. Yeah, because all this is pretty general, never refer to two dimension. Okay, and now I want to show you that given that, for instance, you ask what is the order parameters J when I keep the coupling constant I different from 0. So it's exactly like when I was probing magnetization, which is derivative with respect to the magnetic field, but a T different from Tc. Now, it's just a question of doing, because this is dF over dGj, where you put everything to 0 except Gi different from 0. This is the notation. The notation is order parameter J, which means derivative with respect to the coupling constant Gj. But once you do it, you put everything to 0 except the direction I. Now, if you do this calculation given this form, you realize that this goes like Gi delta I d minus delta J. Sorry, the vice versa. dJ minus di. Okay? You can keep going now. Actually, you can derive everything from here. So what I want to say is that these guys, that previously was my critical exponents beta, you see immediately is an algebraic equation of the delta. Okay? Before, this was defined like, for instance, if I take G to be T minus Tc, before I have been using something like this. check your notes few minutes ago. So, in this notation, GI is playing the role of T minus TC. The exponents beta, I can immediately see how it's expressed in terms of the anomalous dimension. Okay?
Why wouldn't that be
No, from this point of view, no, you are right. Can be whatever. Yeah. From this point of view, is no constraint whatsoever on the values. The only thing I want to say is that from renormalization group point of view, the critical exponents are derived quantity from the anomalous dimension, but not say they have to be rational. Rational is a different story. Rational, first of all, appear in 2 dimensions only, essentially, apart mean field or spherical model or something like this. But this will be part of the story. Why in 2 dimensions has to be rational? Okay? But at this stage, can be whatever. So if delta is square root of the Fibonacci number 100, you get what you get. Okay? So the only thing I want to say from here is that from renormalization point of view, all the critical exponents, you can keep going with these things, are nothing else than algebraic equation of the delta. No. Sorry. The point is, sorry, I'm skipping a lot of stuff. Here, there will be some non-universal number, which are precisely the one of the, but this guy is exactly equal. There is no way, because it's fixed by this dependence. Okay? So, when I'm doing this, I'm skipping a lot of terms. Which are these terms? Is the value of this unknown function computing in 0, which I don't know what it is. So, the constant in front, I don't know. But the aim of the paper I was referring to with Fioravanti and Pascal Simon was to show that if you really look carefully these things, you are able to identify the length dimension, how this quantity depends on scaling. And therefore, you can construct a ratio of them, which are pure numbers. And pure numbers, all of us should agree on that. Because are a number that no matter how you look the system is there. Okay? And the aim of a theoretical physicist is to compute not only the critical exponents, but also this universal number. And once you do this, you have complete control of the class universality. So this is the message. So the control of universality passes essentially 2 steps. The critical dimension, which is property of the fixed point. But the class universality needs also to control around the fixed point. So you have to be slightly away from it. When you are slightly away, you see anomalous dimension ruled by the critical exponent itself, but then by amplitude. The amplitude itself are not pure numbers, but you can cook this quantity in pure number ratios, and they become fingerprint of this class universality. Open and close parentheses, from experimental point of view, is much better the ratio than the critical exponents. The reason is critical exponents vary little if you change class universality, but the ratio can vary enormously. Because the fact is the exponents, as you see, depend on ratio on delta. But if delta has to be relevant, the only value you can take between 0 and d. So the range is limited. So when you cook this, you see that it changes, but they change little. On the other hand, the amplitude in front related to integral of a full function. And there is no reason whatsoever that an integral of full function coincide, because it depends on all possible scaling. Indeed, if you do this universal ratio, you find crazy numbers, as I said, crazy and interesting number. For instance, in easing, if I do in a magnetic deformation rather than thermal, you get as a ratio the golden ratio, for instance. You don't get 1. You get some number which are really pretty significant. Okay? Okay, questions so far? So, summary of all what I say so far is that we had as a guiding line some underlying microscopic system. Nearby the fixed point, this system will have an enlarged symmetry, which is the scaling invariant symmetry. This will be captured by some scaling fields, and nearby the fixed point, this field theory will be described by conformal field theory. Now I start the conformal field theory part, okay? Because means now I want to characterize the fixed point. At this point I have to sit on one of them morally and looking what's going on. Clear? This is the philosophy I'm using. Okay, so now with all that being said, let's therefore start the conformal field theory part. Sure. Shall I erase here or?
No, you can erase it. So you say that the theory is characterized by CFT near the fixed point.
Yeah.
But from the other hand, even if we are, we should do a normalization group for this. But if I look at the critical system and I don't do any normalization group flow, it's still conformally invariant because it's critical system.
If you put the system at criticality. I mean, think easy model in, let's be really operative. You define an easy model on the lattice in the simplest possible way. So, first of all, you decide a lattice. Then you decide the variable, and then you put this one. Okay? So if B is different from 0, you are never critical. So already you have a fine-tuning condition, B has to be equal to 0. If J is not J critical, which of course depends on the lattice, you are not critical. So it means criticality is really fine-tuning. And this is the point. And by the way, this solves the question of irrationality. You will see in a minute. It's a very deep point. Because if the exponents are irrational, there is no way I can close a mathematical object which is an algebra. I should keep going forever. You will see in the due course. But this poses a very deep problem, because to get criticality, I shall making a fine-tuning. I shall choose all this quantity to be 0. Now, as far as you have one variable, it's simple. As far as you have 2, it's more complicated, but you can do it. 3, 4, but when you have infinite number of variables, continuous, how the hell you are going to fine-tuning? So I want to say that conformal field theory with irrational quantities, the way I define later, mathematically exists, but physically has no chance to exist. Because you can never realize it, you see? Because in lab, in principle, you should tune an infinite number of coupling constant to specific point, which I choose to be 0 here, but of course are 0 with respect to a point. So morally, you have to first of all identify where is critical. It's already a spanning. Then you have to put 0, 1, 2, 3, 4, 5, continuously. Impossible. Okay? It's a deep point, very deep point. That mathematically they are allowed, conformal field theory for irrational values, but physically they are essentially irrelevant. Okay? So it's a good point. So it's clear, right? So you're not that critical. To reach criticality, you mean to tune your field to a coupling constant to a specific value. Once you are there, then we are in business. Okay, so now, so the question is, we want to define and solve conformal field theories. So we have to define our we have to define our aims. Now, the part has a very interesting historical background. The historical background is that typically people have approached field theory in terms of Lagrangian. So Lagrangian means you have field, usually scalar, fermions, gauge theory, and so on, in some functional interaction which respects something, right? We are all familiar with that. So if you have Z2 symmetry, the way to construct a theory is representation theory, which is scalar, and then you put an interaction, then move phi square plus a potential. If you have another symmetry, you identify the reducible representation, you construct accordingly. Now, the result of it is Feynman rules. So when you have a Lagrangian, what typically you do is Feynman rules to compute perturbatively stuff. Now, you know that this approach has advantages, but many disadvantages as well. Because apart of the tree level, which after all is classical field theory, all corrections start to pop up infinity. This infinity has really worried for a long, long time people like Feynman, Dirac, Fermi himself, and so on, how to cure it and how to make sense of it. Feynman, Tomonaga, and Schwinger find out how to do it, renormalization group, so it's more or less a change of basis in these things, but it's painful. It's not something cheap to do, and moreover also the understanding is still puzzling. Remember that Dirac all his life never believed in renormalization. Okay, Dirac, one of the greatest minds ever. So I want to say that people have tried to explore different way of solving field theory. And one of these way was proposed by Wilson, Kenneth Wilson, Nobel Prize in Physics for renormalization group idea. This was previous or renormalization group, although it's part of the same package. So what he says is that infinite in the field theory come where you try to put two guys one on top of the other. Because we have continuous set of variables, field is dependent continuous on x, each of x will be an Hilbert space. As far as they are separate, okay, I can handle, but when I try to put on top of it, something happened. And then he said, well, I will make sense of this, namely I will turn the things around, posing the operator Fourier expansion nearby this singularity as a basis from my theory. So it's completely change of philosophy. So the philosophy is in any field theory, once you have order parameters, which here I label generically phi, the object you care about are correlation functions. So you can claim I solve a field theory when you can exhibit to me all possible correlation functions. Okay? Solution of field theory means this. Now, typically, this object you handle in a way or another with some path integral of this type. At least this is a possible approach. Okay? Of course, you can compute it diagrammatically, big theorem, diagram, blah, blah, blah. But I want to say that you should give me a prescription how to compute this object. If you discretize on a lattice, you can do these multi-integrals. Now, what Wilson says that I can compute these objects, which are the key point of the story, if I make as an hypothesis the fact that two fields, scaling fields, which I will redefine again, when xi is nearby x2, has a singularity which are catch up by power law and some coefficients, which will become extremely important later. So if I make the hypothesis that my field satisfies a mathematical object like this, that is an algebra, I have no time now, I will quit, and will be the next time things. What I'm saying is, if you make this hypothesis, of course, any correlation of this will be computed exactly, simply because you can reduce systematically any of these to n minus 1, n minus 2, n minus 3, n minus 4, right? Collecting a bunch of structure constants along the way. At the end of the day, any of these things will be reduced to some expectation value of 1 point that I can prove to be all 0 but the identity. Okay? Is clear the things? So I'm saying this is the object. Typically you compute in certain way, Puffy integral, a big theorem, perturbation, whatever, with some success. What Wilson says that nearby the fixed point, so I have to build up a lot of hypotheses, the field satisfies an algebra. If this is true, and I know all the quantity which are reported here, structure constant and this, the anomalous dimension, then correlation function will be reduced to bunch of structure constant times expectation values of operator. And I will show you that expectation value can only be the identity. It's the only one which survives. So at the end of the day, any correlation function is bunch of structure constant. Okay? So from this point of view, if I'm able to compute C and delta, I'm done. So my aims next lecture will be to build up a scheme that self-consistently can compute the structure constant and the delta, and show you that there are many infinitely set of this quantity which stay up consistently. From this point of view, the word bootstrap, conformal bootstrap, means I can find for you consistent theory, bootstrap, that stays up on its own logic. And we'll see that there are infinitely many fixed points that we are able to classify. Okay? So we'll stop here now, and questions?
What does the mean X one compared to what?
Compared to the correlation length. Yeah. Because back in your mind, you have that you have always a correlation length of your system, which is infinitely many large, although in this scheme you can keep finite. So if you want, the real statement is whenever xi minus xj divided by xc is going to 0, this equation should hold. I have to, of course, I have to build up completely my hypothesis, theory, and this and that, but this is about the scale I have always in my mind is the correlation length, which is large enough so that I'm in the scaling regime. Remember, back in my mind, I want to disregard details of my lattice. So correlation length has to be large enough to do that. In this, it's enough to be finite as soon as it's large. Because in any case, what matters is this ratio. That you can mean it. Either C is going to infinity, or this keep fixed, you are going shorter than the correlation length. Okay. Yeah, thanks for the question. Yeah, what I'm describing is things at equilibrium. Equilibrium means morally all correlation functions described in this way where time plays exactly the same role of a space. So I'm the Euclidean. So your colleague is asking what is the role of time in this scheme. Now, if you are in real life, time rules the evolution. So you might be out of equilibrium and reach something T infinity. In the series of lectures I'm going to do is instead at equilibrium and Euclidean. Means that time you have convert to be one of the variable as many as the other by Euclidean rotation, by weak rotation, and therefore I'm complete in equilibrium. Time doesn't exist; is an extra dimension, and therefore I have a Gibbs measure if you want. Okay? Yeah. Thanks.